of the topics which we left off. Let me share with you. These are the lathe machine operations. You can perform a lot of operations on a round um, specimen, round bar. You can see turning, like turning the diameter from larger to a smaller, and tapering and profiling. These bits, they have certain profiles at the end, and cutting tool with a form tool. These are the form tools, and so on. So let's keep moving forward. The next operation you can see is in the machining, is the boring operation. Boring is like a drilling, but it has a larger diameter than the drill bit. So let me show you the boring, how it looks like. So here you can see it's a very large ring shaped, and this internal material has been cut off with a with this boring tool. This is rotating, this machine, and this moves back and forth. So you can perform a large boring operation. Even the boring can be performed by the lathe machine. You insert this tool into the tailstock, and then somehow this, oh, this has a bit, and it rotates. This workpiece rotates, and you just keep on inserting inside, and with the depth of cut you can increase the diameter, internal diameter of the machine, the workpiece. So now old boring machine can be seen here. You see, this is a tip is this, we call this as an insert. This is the whole workpiece, the tool, it has a an insert. We call this tool inserts. These inserts could be having sharp edges, 1 2 3 4, 1 2 3 4, and this is a Allen screw. Usually we have Allen screw, and then the tool holder, actually we put this insert inside. So you, once one edge is blurry, you can use the other edge, third edge, fourth edge. The planer, you can see the table moves back and forth, and the tool comes down. It's an old planer. Similarly, this is a shaper. What happens is the workpiece is placed over here. Let me change the color here. And the tool comes down, and this is the guides. The tool moves back and forth, and the table goes in the z-axis, and make a workpiece of the required dimension. This is a trepanning operation. Drilling. Everybody knows how to use the drill bits and drill machines. It's not difficult, so I'm going to skip. We will perform some experiments, sorry, the problems in a bit, and then comes another machining operation, which is known as the milling machine. I showed you the milling machine upstairs in Q308. And we do have also CNC milling machine at small scale. So this is the end mill. So it has the cutting edges on the face as well as like on the circumference, like a drill bit. So you can cut a rectangular uh, piece from it. And the face milling here, it has all the cutting edges on the face as well as on the sides. And this is slab milling. You can smoothen the flat surface. Millings are used to machine the flat surfaces, unlike the lathe machine, which are used to do the operation on the round cylindrical shapes. So it depends what type of machine tool you need to in order to perform the required operations. But usually for our residential purpose, we usually don't buy these machines for our home repair a little bit. These are usually used at the industrial scale, where you have to manufacture the parts at a large scale if they are expensive. This is the face milling operation being performed here. So you see, initial the height was big, and this the depth of cut, and this and you see the tips. Some of them are diamond shaped. We call this diamond shaped tips. And this is another machine tool which is like horizontal milling. When this um, overarm is horizontally placed, this is a horizontal arbor, and when this is vertical, vertical place like a drill press. Where is that drill press? Let me show you over here. Um, Let me show you on the next horizontal machine. This is an old horizontal milling machine. You have to hold the workpiece in a vise, otherwise you cannot cut it. You have to hold some holding, and this is a vertical machine where the tool is mounted uh, vertically. This a vertical axis here. You can see this axis is a horizontal axis, and this is a vertical axis. So machine tool, when you buy machine tool, you have to see what type of operations you are going to require, whether you need vertical milling machine or the horizontal milling machine. But in our university, in that building, we have seen the vertical milling machine. These are different type of milling tools which perform different operations. You see, these are the straddle milling. The two cutting tools are mounted on the same arbor, and this is a form milling. It has a special form like this contour shape is being machined. Okay, and this is slotting like a band saw. Slitting's like a bandsaw. Slotting is a little bit thicker than the bandsaw edge, you see. Another machining operation is known as the broach machining. You see, like the splines, uh, like a small uh, gear teeth, internal gear teeth. So initially, it scrapes off a small material. Second layer, you see, cut per tooth is very small, but how many teeth are there? One, two, three, four, five. So it keeps on going forward and keeps on increasing the depth of cut as it moves forward to a certain required depth of cut. This reaming operation is like a smoothing the internal roughness, but it is not that smooth like a honing operation. So let me show you maybe a honing operation. Yeah, it's a honing operation. Usually we perform honing operation to a thousandth level. 1/1000th of an inch when you are doing some engine ring piston, uh, rebuilding the whole engine rather than manufacturing the new engine. You just rebuild the old engine to a bigger size, a little bit bigger, because you are cutting off more material to a precise further new shape. So you need to honing operation is just so. Another operation for cutting is like thread taps and dies. I have used them, and you should, being a mechanical engineer, you should also know how to use them. We have taps which are used to perform the internal threading operation, and the external you can perform like a screw on the die. So why do you want to machine? These are the reasons that you have more control on the shapes. Mirror can be cut to 1/2 wavelength of light. They are highly flexible. These are the reasons. I would highly recommend you, when you go home, read the reasons. I'm going to skip some descriptive slides, and I will go to the analysis. How to how to find out the cutting forces, thrust forces on a tool. So you see, these are the trade-off. I want to read this slide. Low cost tool versus machine tools, high production rates, and low tool life. Machining is very highly wasteful operation as compared to the rolling. You see, the rolling operation, nothing is lost, no waste. You just have to deform the shape. In the machining, they are highly wasteful. Chips are going everywhere. You are losing chips, but these are the scrap. Okay, please draw this diagram of the cylindrical portion which is being turned down to a smaller diameter. So material removal rate is very important, and this is also known as the Q. Q equals to velocity times area, or velocity time area. We will be finding out the MRR, material removal rate, how much uh, material is being removed per second. That can be found using this formula: speed, surface feet per minute. We call it how many feet per minute, and the feed and the depth of cut. Make sure you understand the concept here. This is the depth of cut which you already which you decide how much depth of cut you need to give, and then you start moving the tool. Suppose after some time it comes here. Okay, so in one revolution, how much feed has been given? Maybe like 1 millimeter per revolution. So this is, if you take a look, so the chip which is coming out, it is B, the width of the cut plus depth of the cut. I'm gonna show you in more easy way later. So F is the distance of tool, per revolution. You see, I just want to show you the distance of the tool per revolution. D is the depth of cut. S times F used for optimization of cutting, depth of cut fixed by initial and final dimensions, limited by the cutting tool life. Some of the range of operations you can perform ranges goes from cutting speed goes from 1 to 2000 surface feet per minute or 5 millimeter per second to 10 meters and so on. And feed is like 5 ten thousandths to 1/10 of an inch per revolution, or 13 microns to 2.5 millimeter in this turning operation. So the depth of cut can go up to 1 inch, and volume of the material removed, material removal rate can go range is usually greater than 100 inch cube per minute or 28 centimeter cube per second, typically from 5 to 10 inch cube per minute. Okay, we have talked about the lathe operations. Now let's try to understand some of the technical details of the milling operation. This is also orthogonal. It can be also orthogonal cutting can also be performed with a lathe as well. Over here, because we assume this looks like an oblique, but let me tell you the orthogonal. As I mentioned earlier, this is the tool piece, cutting tool. I suppose this is a large piece here. The tool is advancing here, and the chip is going up, VC, and this is a cutting velocity. Tool moving, cutting tool moves up. You see, this is the force, shear zone. We call a shear zone where there is a cutting operation happening. You see, so, and you will see that this uncut uncut chip thickness T0, and thickness of the chip is TC. TC is greater than T0. Orthogonal means that the tool cutting edge is perpendicular to the cutting direction. Tool is moving like this, and this is perpendicular. Cutting edge is perpendicular to the tool direction. The process adequately represented by two-dimensional geometry. This is the cutting edge, this is a cutting edge, and the tool is moving perpendicular to the cutting edge of the tool. This is orthogonal cutting. Tool is perfectly sharp. Tool only contacts workpiece on its front rake. So the rake is the angle between the between vertical. Suppose if you have this kind of tool, and the rake angle is, suppose this is my rake angle here, and in this case, suppose this is the vertical, and this is the front face, and the vertical is the rake angle. Primary deformation occurs in a very thin zone adjacent to the shear plane. Cutting edge is perpendicular to the cutting direction. The chip does not flow to the side. What I mean by that, chip does not flow to the side means that it goes directly above the rake face. But what happens if it is not the cutting edge like this and the tool is moving like this? Then what will happen that the chip will come here and it will move to this side. You see, if the cutting edge is like this, like you imagine you are just pushing the hand at an angle and that you have more air. The benefit of this one is that larger area will reduce the shear forces force force per unit area. So larger the area, this pressure is the shear stress is kind of reduced. But that's an oblique cutting. But I will focus more on the orthogonal cutting. But I will show you some of the terminals. Yes, please draw this diagram. And with this diagram, you will understand some of the nomenclature of the, okay. So for this is orthogonal cutting operation, and the direction of the cutting velocity is perpendicular to the tool. Maybe this is the tool, okay? Maybe it's the tool. Okay, now chip thickness is after tool has cut the chip, so it's TC. Uncut uncut chip thickness, rake angle, clearance angle, and the cutting velocity. You can control them. They are independent variables. And the dependent variables are the shear angle, which is horizontal to this shear plane where there is uh, cutting happening. And this is the cut chip thickness. Let me show you next slide. When you go home, you practice. Okay, this will help you. I'm gonna perform today. I will solve a few problems for you. One is the positive rake angles is angle when this is less than 90 degree. Over here, this is about this positive rake, and sometimes the tool is like this on this side. Let me show you another. It has sharp cutting edge, reduces shear plane and lower strain, and another benefit, low power consumption. And negative rake angle when the cutting edge is on the other side of the vertical axis. It increases the shear plane size, can be turned over, yielding twice as many edges. Okay, we already have drawn this picture, right? So let me go to some of the formulation. How do you get this ratio? Look over here. I'm going to focus. This is like a shear plane, and you will draw a perpendicular here. What is T0? So if I make this triangle outside this figure, this is my A, B, and this is the shear angle, and this is 90-degree, and this is the T0 uncut chip thickness. Okay, now over here, what is my T0 over AB? Opposite over hypotenuse. Agreed? So T0 would be equal to, that means T0 or T naught equals to AB sine phi. This is what it is. Okay, this is about the TC. So for the TC, what you have to do here, look over here, this is my, if I draw another triangle here, draw perpendicular here. Okay, this is very rough and perpendicular here. This is the chip thickness, so I'm going to drop perpendicular here. Okay, so this is my alpha angle. Okay, and what is this angle? This angle is, take a closer look, this is 90-degree. Agreed? This is 90 minus alpha, 90 minus phi. And if this is 90 minus phi, what is this angle? You will tell me, professor, this is 180 minus 90 minus phi. I would say just like that. Plus, agreed? And if I do the math here, would it be phi minus alpha? So this side, this angle is phi minus alpha. That's what it is. So if this is the right angle triangle, this is the opposite over adjacent. So I want to show this, this remains hypotenuse. AB is the hypotenuse for the other triangle as well. So this T0 TC is very blurry. Let me rewrite here. This is, sorry about this. This is TC, cut chip thickness. This side is, this side is TC. Agreed? TC. So this triangle, let me break it outside, bring it outside here. So this is 90-degree, and this is AB. Okay, BA. So I want to know what is TC. If this angle is given, phi minus alpha. Agreed? So you will tell me, professor, this is adjacent over hypotenuse. So adjacent over hypotenuse. What is adjacent over hypotenuse? Cosine, cosine that angle, phi minus alpha. Agreed? So cut chip thickness equals to AB cosine phi minus alpha. You agree with your professor? So that's how you write down. So T0 over TC equals to, I will say AB is cancelled. So let me write down AB sine phi over AB cosine phi minus alpha. Agreed? This is cancelled out. So this is the ratio. You cancel this out. Do you understand that? This has not been explained clearly in the slides, but I wanted to explain it to you guys over here. And then now, how do you get this tan phi equals to R cosine Let me share with you. So, okay. So the way you will do this from the previous formula, let me show you over here. This formula, you know, cosine, you know that trig identity, cosine alpha minus beta, cosine alpha cosine beta plus sine alpha sine beta. Agreed? So now I'm gonna choose this one. So let me write down how do you get this formula here. So R equals to T0 over Tc equal to sine P over cosine alpha, cosine phi cosine alpha plus sine phi sine alpha. And then what you can do here, bring this sign over here under this one. So in the next step, I can write down here 1 over cosine. Rather than cosine, I would write down cosine over sine. Let me write down for completely so that you should understand. Cosine cosine alpha and sine phi sine alpha sine phi. That sine phi in the numerator is in the denominator now. Okay, so this becomes 1 over cotangent phi cos alpha. This phi is cancelled, so you're left with sine alpha. So we want to get this formula, okay? So if I flip this up, so can I write down like this? 1 over r is if I flip both sides, cot phi cos alpha plus sine alpha. Now over here, if I bring this sine alpha, negative sine alpha here, and negative sine alpha here, then I can rewrite the whole equation. I can rewrite the whole equation like this. 1 over r minus, so let me rewrite it. Cot phi cosine alpha equals to 1 over r minus sine alpha. Or you can further simplify this like this, 1 minus r sine alpha. And if you bring this in the denominator, so you can write down cot phi equals to r cosine alpha. Agreed? And now cot is 1 over tangent alpha, tangent phi. So tangent phi equals to r cosine alpha over 1 minus r sine alpha. It's the same thing which we just studied earlier. So let me show you. This one is the same thing. Do you understand that? This has not been explained in the slides clearly, so I wanted to give you further insight. How do you get this formula? There is another formula for the geometric shear strain. So I think you don't need to derive it. You just remember, you can write it down. It's not that important. So I can write down like this. So if alpha is 0 in this formula, if alpha is rake angle 0 means this edge is like this, okay? This rake angle is 0. If alpha is 0, then phi, as phi increases, the shear strain decreases. You remember shear strain, if you have a, if you remember shear strain, you can two parallel forces of same magnitude but opposite direction, you can push this over here and this one. So this is the shear strain. Suppose delta L over L. So shear strain equals to delta L over the perpendicular distance. And you remember, like, sigma equals to E times epsilon. This is in the stress relationship. This is the in the shear strain. Like over here we have shear stress equals to, this is the compressive or the tensile stress, which is equal to E. Remember that. It's very like this. This is my elastic modulus. This is my strain. This is my shear modulus. G is my shear modulus, where gamma equals to shear strain. Have you studied these before? That's good. In general, these are the variable that as you increase the phi, the shear strain decreases, like over here. And as you increase the rake angle, the shear angle decreases. As the chip thickness, cut chip thickness is greater than uncut chip thickness. So usually this the shear strain is in the magnitude of 2 to 4. So for example, this was my, it's going up. You moved it upward, okay? You moved it, you push it upward, you created a strain here. So I would say this is my delta X over D. So shear stress is delta X over D in the shear strain, sorry, delta X over D. It's not that important, but it's the dimensions. Like it goes from 2 to 4. Now let's do the next analysis for cutting velocities. Please draw these diagram. This is cutting velocity. How do you get this cutting velocity? A diagram is going to help you in our formulation. So let me show you. When the tool is, let me bring this diagram in front of you. For instance, yes, this one. So let me bring this over here. So this is a cutting velocity diagram, and this angle is phi minus alpha. It's not difficult. How do you get this phi minus alpha? I can show. So let me explain to you. The cutting speed is, this is the tool moving forward with a cutting speed, okay? V. And V VC is the velocity of the chip. The chip is going upward on the rake face of the tool, going upward. So VC is this vector. Agreed? This vector is VC, and this vector is the tool moving forward. Agreed? And this is the VS. The shear is, this is the cutting is happening in this direction. You are pushing it upward. Okay? Your cutting is happening, the shear velocity. And there are certain relationship. So how do you get this? So if I show you, this angle is phi. Agreed? This angle over here is phi. It's phi over here. And this is the straight line, vertical axis, and this is a vertical axis. So if I draw a vertical axis here, vertical axis here, let me redraw it here. So vertical axis here. So this is my rake angle because the chip is moving on the face of the cutting tool, which is the rake angle. Agreed? And then suppose this is my x. Angle is x. I'm gonna show you how do you get this angle phi minus alpha. So if this is alpha, this is 90 degree, okay? Because we assume this uh, they're at 90 degree. So what is this angle? So this angle is 90 minus alpha. Now this x, you can find out, look, 180 minus 90 minus alpha plus phi plus x. Agreed? So you can write down 90 minus uh, plus alpha minus phi plus x equals to 0, or x equals to, did I make a mistake here? Yeah, this should have been negative sign here. When you open the parentheses, 90 plus alpha minus phi, and x equals 90 plus alpha minus. And if you do the math here, this is the x equals to this one. So you can also do this 90 plus 90 minus alpha plus x. What did I do? I'm sorry, this is not a good. I was thinking something else. Yeah, this is wrong analysis. This is correct. So let me show you. What is VC over V? VC over V can be written as this formula. Remember I showed you earlier that this ratio, yes, this ratio. The chip thickness times the velocity, and then Vs over, you remember, is opposite side. You remember sine opposite angle. What is the opposite side here? V sine V minus alpha. 90 minus minus V minus alpha. Yes, now it's clear. So look, what I did, law of sines. I apply the law of sines on this velocity diagram, and then sine 90 minus alpha is equal to cosine. Let me rewrite here for your help. So Vs over, I can write down Vs over cosine alpha equal to V over cosine V minus alpha. Agreed? Or you can write down Vs over V. Vs over Vs. You just cross multiply this, okay? You get the same result. You bring this down, and that way you can find out. So this is the derivations. Then comes another interesting thing, that the shear strain and the shear strain rate of shear strain can be found using this. It's very, very high, 10 to the 5 per second. High shear strain, the shear zone, it goes from 1 to 6. Okay, this is the card models, like we play cards, and what happens that these are the small cards coming. Before that it was here, but now it is being lifted upward, so it's now shearing. Either these are the parallel cards. We assume that the chips which are forming, they are like very small cards parallel to each other. That makes our analysis very easy for shear strain. So the card model, and this is the rise perpendicular distance, which is this dimension, and the width. So perpendicular distance is d, and the vertical distance is x. So it's about 2 to 4 magnitudes. So we have done the analysis. Now let's do one problem. We will also see in this slide that what is oblique cutting, some of the parameters here, idealized chip formation. Is the same diagram, so I'm skipping faster. Let's come to the question. The cutting energy and the power, the power equals force times velocity, correct? So here, this is power equals force times the speed, SF PM, or power equals torque times omega. You should know these basic formulae. And energy per unit volume can be achieved using the area under the curve, stress over strain, and energy is, we call this U as energy per unit volume. The volume of the chip being removed, volume of how much energy required to remove that much volume is U. And MRR is volume per unit time. So can I write down power formula as, which is W, energy per unit time, or energy times MRR. So if I ask you what is the power required for removing that money, that much volume of the chip, so you will use U times MRR. Okay, U is the specific energy or energy per unit volume. So I would say joules per meter cube times meter cube per second, because MRR is Q, which is velocity times area, or this is in watts. So make sure you understand this formula here. So energy per unit volume is U. Okay. Energy to form chip divided by volume of the chip, work per unit volume. This is the formula of the energy power times the time and cutting power. Yes, this formula you will be using in most of the homework problems. Power required to generate that much energy, the chip removal, U times MRR. Let's compare some of the energy required to generate that much cutting operation from 0.5 to 0.48. Suppose if you want to turn down the diameter of a cylinder uh, specimen here, or axial bar, so you want to reduce to the new diameter. Final diameter is how much? 0.48 inch, and initial diameter is 0.5 inch, and the length of this billet is L0, 6 inches. What is the energy required using the tension formula? And you remember energy required in the tension, work per unit volume, average. If I go back to my lecture, I believe I have explained this over here. We did this in our first lecture. Let me grab this formula here. This is just for the review purpose that we have done this work under the area. You integrate that area, and this is the power law which you will apply here for sigma equals to in this plastic domain, and you get energy. You understood this is my U, correct? Now you will use this formula to find out U, and this is known as the work under the tension. So what is that formula? So let me show you how will you use. Can you find out, do we have K value? Let me see if we have the K value in our next slide. Yes, we do have our K value in our next slide here in epsilon. Can you open your calculators? Let me know what is the, so epsilon 1 can be found using this formula, ln initial area over the final area. Initial area is pi by 4. Let's remove the pi by 4 because it is same in the numerator and denominator. So I can write down 2 ln d0 over df. D initial is 0.5, d final is 0.48. 2 times ln 0.5, 0.48. What do you guys get? Do you get 0.0816? Please confirm. Yes, he says yes. So let's move forward. So now we want to find use this formula. After this, use this formula. We already found the epsilon 1. Use this. K is given in psi and n is given. So let's use energy per unit volume 185 10 to the power 3 0.0816 n plus 1 raised to power n plus 1. So I will say 1.45 agreed, divided by 1.45. And if you solve for this, you should get 3371 kilo psi per unit inch cubed. Agreed. So now we have to see what is the energy. This is energy per unit volume. So energy per unit volume equals to U. Agreed. So what is the volume? You will tell me, Professor. Volume is area, initial length. Initial area is how much? Pi by 4 d naught square L naught. So I can write down pi by 4.5 square 6. Correct? You agree with me? And then you will write it down. Energy. That means we are interested. That means energy equals to U times volume. And U is 3371 into 10 to the power 3 times this volume. What do you guys get? Do you guys 3970 pound inch? Please confirm this. This is an inch square. And how do you go from pound inch to Newton meter? So 1 pound force equals to 4.45 newtons. Agreed. And we want to go from here to Newton meter it for our convenience later down the road. So I can do the math for you, or you will help me. Okay, Newton 1 meter equals to 3.28. Sorry, 1 meter equals to 3.28 feet, and 1 foot equals to 12 inches. So you can go from here to meter. So let me write down here 3970 pound force inch, and let's convert it into Newton meter. So 1 pound force equals to 4.45 newtons, and 3.28 times 12 inch equals to 1 foot, sorry, 1 meter, 1 meter. And then this is cancelled, inches cancelled by inch, pound force cancelled by pound force. You are left with Newton meter. So if you do the math, can you help me? Can you help me with this method? And if you do the calculation, do you get 449 joules? This is the energy required when you deform it by deformation process. You see, we call it the drawing process. You agree? The same answer you get. So one student verifies. Akil says yes. Demetrius says yes. Okay. So let's go to the next part. Is this is by the internal deformation. you are pulling like in the machine tensile stress. You remember? Now the question is, do compare the energy required in deforming the material from in in deformation versus machining. And you will tell me, you use the cutting tool now. Okay, I'm gonna cut this billet of 6 inch long. This is my 6 inch long, and now the tool is coming here. The tool is coming here, and it's gonna cut it. The depth of cut, the new diameter, I will say yes. The new one is, how much is this? 0.48. And how much is this? 0.5. And energy equals to U times A naught L naught. A naught L naught is even. And for the shear energy, you should have been given this energy. So let me write down the shear energy. It is 594,000 pound force inch per inch cube. Let me share with you this. This is not given here. Yes, let me share with you. And this much, initial minus final area times L. Energy equals to 594,000 times 5 by 4 d initial square times the length. If you do the math here, you should get 554,650 pound force inch. And how do you go from here to Newton meter, which is joules, 6,176 joules? Over there, the energy required was quite low, but here is quite high. Comparison. In tension, the energy is 450 joules above, and in the cutting operation, this is 6,176 joules. I would say when you go home, practice this problem again. I'm going to open this homework for the machining operation, and we will solve from here on, let's say, next week.